I'm going to try to stay in between. Please object if there's a problem. So let me start about two-body and the three-body problem. And start from the Newtonian formula, produce the known Lagrange perturbation equations, and then introduce Hamiltonian formulas to discuss this. And the thing that I want to do is to discuss a little bit about the disturbing function and its structure, and about the basic tool that we use to do perturbation theory with canonical transformation. Again, I'll stay on the surface more or less, and try to introduce a couple of applications. I cannot do that in 40 minutes, but maybe Alessandra will give me a few more minutes. Now, this is too dense because it's too simple. This is the equation of relative motion for the asteroid in the Sun, and as I told you, the formal solution is a vector function which contains the 6 elements, and this is the velocity. Now, if I introduce a small disturbing force and assume that the elements are now functions of time, this is the equation of motion, and I can take the derivative of this, which has inside the derivative of the elements. And in order to solve the system, you need to make an assumption. You need to choose a specific gauge. As, by the way, the equations are copied from a paper by a French in Goldreich, which I found very pedagogic. You can check it out. And this condition is that you need to amend to the system in order to solve it, and it is the so-called osculating condition of Lagrange. But the orbit that you will find would be tangent to would be an osculating ellipse that would be tangent to the real orbit at any time on the point that you choose. So to solve that, you take the second derivative and you plug it in, and you remember that f actually satisfies the homogeneous system, so you end up with this set of equations along with this constraint. Now, if you multiply this by dGdC and this by dFdC, and you subtract them, you find this form, which is the general form of the Lagrange perturbation equations, these being the so-called Lagrange bracket, which gives the derivatives of f and g with respect to the elements. Okay? So if my disturbing force is actually the conservative force, that is, it can be produced as the gradient of a scalar function that depends on the coordinates of the asteroid, then you get the nice Lagrange equations. Beware of the sign conventions. As I come from physics, I'm used to this. In most books in celestial mechanics, here it's simply the gradient of a function r. Okay, so the signs can be really tricky. When you read a book, be careful with that. Now, in the spirit of analytical mechanics, we can get the equations of motion instead from Newton's equation from a principle which is called the adiabatic principle that gives you these general Lagrange equations for a mechanical system, this small q being the generalized coordinates, q dot being the generalized velocities, the derivatives of q, and capital Q being the generalized force. Okay? And if f is conservative, this is, let's say, simplified, or it becomes more elegant in the sense that this is the equation if I introduce a Lagrangian function, which is just the kinetic energy minus the potential energy. Okay? This is the kinetic energy. Now, I can define the Hamiltonian function for this system from the Legendre transform of the function L through this by introducing the momenta through this relation, the generalized momenta. There is, of course, a fundamental principle of mechanics that typically when you teach this course, you teach it later. And it says that from all the orbits that the system could choose to go from Q1 to Q2 within a given time, T1, T2, it actually chooses the orbit that satisfies this, that is, the action integral is stationary. And there is a theorem in the calculus of variation by Euler ensuring that the orbits that satisfy this are the solutions of this. Okay? So, formally this is complete. I'm actually only pointing out this because I'm going to use it a little bit at the end. So if I want to write the perturbed two-body equations in these formulas, again for a force of this type, I'm just plugging it here, and essentially the potential now would compose of the Kepler potential and the disturbing function, and the same holds for the Hamiltonian. Like that. And the Lagrangian equation, of course, would be in this form. Here I will have the derivatives of the disturbing function, which is actually the same here. I have the derivatives of R with respect to the elements. Now, R is called the disturbing function, and it's a name well deserved because it can be really disturbing up to frustrating sometimes to use it. And in order to use it here, you need to know the transformation, of course, from the generalized coordinates to the elements. Now, there are different sets of oscillating elements that one could use and plug it here, which would simplify or not the equations. For example, if you choose the Delaunay elements, which are the mean anomaly, the argument of perihelion, and the longitude of the node, just with different symbols, L, G, H, and as momenta, let's call it, you choose L capital, which is square root of M. The mass, mu is the mass of the sun, if I forgot to say. G, which is the modulus of angular momentum, essentially, and H, which is the Z component of that, the Z projection of that. You will see that the Lagrange brackets simplify a lot because only these are 1 and the rest are 0, so you end up with this system. So these are just the partial derivatives of R with respect to the other 3, and these are the same with minus. So it's a clearly canonical set of elements because the system of equations produces has the same structure as a symplectic system of differential equations or Hamiltonian system. Okay? The same holds for another set of variables that you will see many times, which are the so-called modified Delaunay. So, the network came. So I'm going to kill it now. And again, in different books, you will find a little bit different names. You will find it as modified Delaunay or Poincaré elements. And they are just, you can derive it from the usual Delaunay elements by simple contact transformation. Okay, so here the angles are longitude. It's the mean longitude, it's the opposite of the longitude of perihelion and the opposite of the longitude of the node, conjugate to these 3 momenta, which for small eccentricity and inclination are just proportional to E square and I square. So if I use these elements and I try to plug it in and compute the Hamiltonian of the two-body problem is this. It's very simple. The Keplerian Hamiltonian depends only on one of the momenta, the degeneracy of the problem, and the disturbing function would be a function of the elements of all the elements. So this is perturbed Keplerian Hamiltonian in Delaunay elements. I wonder why it doesn't work, of course. Now it's frozen somehow. Okay, came back. Now, to go a little bit deeper in the Hamiltonian form is, of course, I didn't say before that if you have the Hamiltonian function that defines your system, the equations of motion are just these, the canonical set of equations. And the total derivative of H over time is actually the partial derivative because the rest of the terms cancel out because of this. Now, if the system is autonomous, so it does not depend on time, or you can make it autonomous by extending to free space, the Hamiltonian is constant. Frequently, if you choose the coordinates nicely, and you are in an inertial frame and so on, this is just the total mechanical energy. Now, also, if there are ignorable variables, meaning that one of the variables is missing from the Hamiltonian, then the respective momentum is an integral of motion. I can rewrite a little bit the equations by introducing the so-called Poisson brackets, which are the derivatives of f and g now, multiplied here, with respect to q and p. Okay. Then the equations of motion can be written as this. The time derivative of q is the Poisson bracket of q with the Hamiltonian. The same for p. And the fundamental Poisson brackets, which are these qy, pk, should give you, as a result, the Kronecker delta. So it's either 0 or 1, depending on what you choose. This is important because it can be used as a criteria later on to check if a transformation is canonical or not. Now, for any function of the phase space variables, the total time derivative is equal to the Poisson bracket with Hamiltonian, which can be viewed as an operator acting on f that we will call the dh operator. Then you have df dt is some operator times f. Can formally integrate that by bringing f here and putting dt on the right-hand side to get the formal solution, which is the Lie series of f under the t flow of the Hamiltonian h, and it's this. So the solution formally is that if I have an initial condition, then I apply this operator and I get f. This is conveniently symbolized like that: a series of f with respect to h and t. Now, in celestial mechanics, you probably know, we love doing transformations. We love changing variables. It's our hobby. It's not a hobby, it's a necessity, actually, because you try to find the solution more easily. Okay? Hopefully, you can make it in a very simple system by doing transformations, but it doesn't always happen. But we work on a restrictive class of transformations which are called canonical, meaning that they preserve Hamilton's equations. So the new variables, capital Q and P, should give you exactly the same equations for the new Hamiltonian H prime. And if the transformation is time independent, most of the time, the new Hamiltonian is just the old one written in the new variables. Now, how can I find these transformations? Well, one way to do it is that you know that Hamilton's principle should hold in both cases, which means that the integrands here could not differ more by a total time derivative of a function of two independent variables, and you can pick either the old Q's and P's or the new Q's and P's or mixed type functions. These are called generating functions, and you can show that if you choose, let's say, a generating function of type 2 that is a function of small q and capital P, the old variables and the new momenta, then these equations would give you the transformation. And it will be canonical by construction. So the new variables would satisfy this. Simple geometrical transformation like translation, going from Cartesian to polar and so on, can all be done this way. We know the generating functions have been used for hundreds of years. Now there's another way of doing it, well, a little bit more involved, where you can look for a generating function of the new variables, let's say, this. And there is, theorem says that if such a function exists and a small parameter exists such that the old and the new variables can be cast in this form, then the Lie series denoted by these equations define a canonical transformation, meaning I have the old variables and momenta, and I find a generating function that does what I want, the transformation I want, over a small parameter. Then I compute the Lie series of this quantity, and this gives me the transformation to the old variable. The same for P, and here inverse. Of course, you can also invert that, but if you are tempted, for example, to use this transformation direct and the inverse transformation in order to relate the new variables and the old variables in both senses, then you have to compute an infinite number of terms or forget about it. This is a very nice comment, a very nice explanation given in the famous paper by Milani and Knežević on proper element theory, where they do the transformation, I think in the opposite sense, because you want to determine the proper elements knowing the mean elements. And then they discuss the problem of going back and show that exactly if you cut the expansion at some point, the two transformations do not give the same result. Now, an interesting example of using this. I take the simple Hamiltonian of the simple pendulum, which has this equation of motion. So 1 degree of freedom system is integrable because it's independent of time and has one integral already, the Hamiltonian itself. Now, I use a generating function of this type in order to do a transformation. So basically, I take this product. If I cut it here, the transformation is just the identity transformation. Q prime equals Q, P prime equals P. And then I add a small parameter, ta, times the Hamiltonian itself, but written in mixed variables. Then I can take the equation of the transformation and find, if I work it out a little bit, that P prime equals P minus T this, and Q prime equals Q plus T times P. So essentially, this is like integrating this equation for a short time, T, tau, okay? And this is more or less the same, because here, in the Euler method, I should have here P and not P prime. This is sort of modified Euler method. I think it's actually called Euler-Hund or something like that in numerical analysis, I'm not sure. That is more accurate than the kind of midpoint method. Could be. I'm not sure. The thing is that you can look into this transformation as a transformation that takes the old variables and advances them a step tau in time. And these are your new variables. And because the mapping is by construction symplectic as it is the result of the canonical transformation, it can be called a symplectic integrator of order tau for these equations. And it's a method that has been used, for example, in astrodynamics in order to produce symplectic mappings that are much faster to solve than numerical integrations 20 years ago. Okay? Now there is a catch here. You should be careful. The pendulum is an integrable system. It's a 1 degree of freedom autonomous system. And the 2D mapping that you construct here is very well known, is the standard map, which is a prototype of chaotic motion. So while the original system doesn't have chaos, this system has. And one should be very careful when using this tool as an integrator for the original system. A better way to do it is ask for an explicit transformation that takes you from the old variables qp to the new variables q prime, p prime, and approximates the formal solution for a time step tau up to some ordering. Meaning you take this and you want to cut it at some point and to use that canonical transformation as an integrator. Basically what you have is this Hamiltonian which has an operator dh that can be split into, it's the sum of two operators, tau and p. And it's easy to see that if you would have only tau, only t, sorry, I'm mixing Greek and Latin symbols all the time, doesn't it? If you use only t, the kinetic energy, so you have only the operator dt, you have half your Hamiltonian, and it's completely integrable, of course, and you can solve it. Meaning that it depends only on half of the variables, so the other half are ignorable, so these are constants. Okay? But if I have only q, it's the same, but it's the other half of variables that are constant. And I can compute the solution. So half of the Hamiltonian I can compute explicitly. The other half I can also compute explicitly, and it amounts to applying these operators on the original initial conditions. And if you are tempted to say, okay, so I apply half first and then the other half later and I find the solution, it's of course not true, because otherwise all Hamiltonian systems would be trivially integrated. Okay? And the reason why it doesn't hold is because the composition of these two symplectic operators, which is this product, okay, gives the exponential of another operator, but this is not dh. If this is t and this is v, this is not h anymore. The Baker-Campbell-Hausdorff formula for operators says that if the operators do not commute in general, this is the result. T plus v operator would give you a z operator, which is not the Hamiltonian, but plus higher order terms in time. Actually, if you can compute the commutators here, just the first one, you can start from the BCH formula, apply T separately, apply V separately, then apply the commutator, and you can see that the previous formula means that you're not solving your Hamiltonian, but you're solving a new Hamiltonian, which is H tilde, that it's not T plus V, but plus these errors, let's call them terms. Okay? The value of this is conserved to mass simplicity, but not the original. However, in most applications, these terms that you meet, if tau is small enough, nobody knows what that means, would be oscillatory, which means that the error in the integration would be bounded. And that's a desirable property if you want to integrate for time equivalent to billions of years. Now, you can find higher order integrators than the first order in tau by saying, okay, now I'm going to take a product of these many times, and I'm going to put some coefficients in front of each exponential, and I'm going to try to find whether this product can cancel out some of these terms, so that if I cancel this term and I cancel this term, the error is order tau to the 3. And I'm happy. To do that will mean you will have a system of these numbers. This is an algebraic system, which is not linear, of course, but can be solved to determine CIs and DIs in order to cancel some of the brackets here and get a better approximation. Now there's another way of doing better. If your problem can be cast in this form, so an integrable Hamiltonian H0 plus epsilon and a perturbation that depends only on the coordinates. Let's say the Kepler problem, the mass of Jupiter, and the perturbation. It's in this form. Then you can show in exactly the same way that if your operators are solving H0 exactly and H1 exactly, then doing a composition would give you this Hamiltonian preserved, which is the original, plus, of course, the error term, multiplied by epsilon. So if the mass of Jupiter is 1,000 times smaller than the mass of the Sun, this is a much smaller error than if you would split the Hamiltonian with T. Okay, this is called mixed variable splitting. Essentially, it means that if you want to have the same error, you can increase your time step by a lot, by a factor of 10. These are two figures from two old papers. This is from Yoshida, the guru of symplectic integrators, as we all know. So this is a fourth order symplectic integrator of the T plus V type. So you have actually a product which has 6, if I remember correctly, operations. This is the zero line, and this is the error in the original energy of the system, which, as I told you, is bounded. So on the long run, it outperforms a Runge-Kutta method of the same order, for which the error is decreasing. I'm not exactly sure which system is. And if you want to see the result for an integrator of the other type, mixed variable splitting, Keplerian plus interaction, this is, for example, from a paper introduced by Lee et al. Introducing the Simba integrator for planetary dynamics. And the error has exactly the same behavior, only this is a zoomed version of that one. Okay, so the relative error in energy is of the order of 10 to the minus 6 for this time step, and it holds for several thousands of millions of years. Now, since I have time, I can give up on the Hamiltonian formalism and start discussing a little bit the disturbing function. The main two problems that I promised to talk about in the school, but I'm not sure how far I can go on both, is the satellite problem and the asteroid. Now, on the satellite problem, you have an artificial satellite moving around an object which is not spherical. Okay? But if it's not too far from spherical symmetry, the potential can be cast in this form. Okay? This is the spherical harmonics expansion of the potential. The zero order term is the Kepler part, and the rest are deformations only in latitude or also in longitude. So the zonal terms, tesseral and sectorial terms of deformation are given here in this series. If you want to see the expansion, please see the book of Kaula. I cannot do it in 4 hours, of course. Okay? But I can tell you a little bit of what is the machinery behind it. You have these terms, which is 1 over r to some power. Okay? And if you substitute there the expression of r in terms of elements, you have to start by binomial expansion of this function. And then you have here trigonometric terms that, if you want to translate to elements, you need to start, for example, with a little bit of spherical trigonometry here to relate the latitude to the inclination, this angle, and the longitude of the argument of variance. Then somehow you can manage to do a Fourier expansion of this thing, which will be something like that. This is from the book of Kaula. Theta is time, sidereal time. The rest are the elements of the satellite. And the expansion is hidden in the very elegant names F and G, which are the eccentricity and inclination functions, and are notorious expansions in these two quantities. Now, if you want to start by simple approximation, it's not that bad. The simple J2 problem, for example, is the problem where you assume that the central body has an equatorial deformation or mass around it, like the Earth, equatorial bulge, and that the only sizable coefficient is the first coefficient in the spherical harmonic expansion, the so-called J2. Then the Hamiltonian written in the Cartesian variables, as before, is this. this epsilon term is actually the dimensionless coefficient J2 times R squared, the mean equatorial radius. And this is the Legendre polynomial of Zine phi 2, 0. Now, I do what I said. Mainly, I change that into orbital elements using spherical trigonometry. I plug here the equations relating R to the elements, and I do expansion. If I want to check only the long-term evolution of the orbit itself in terms of size and orientation, and not exactly find the position of the asteroid, of the satellite, of course, right, on the orbit, I can take an average, which is another discussion we'll have to do tomorrow, over the fast angle that I want to ignore, the mean motion of the sun. Then the Hamiltonian in Delaunay elements take this form. And it's a very nice Hamiltonian. You can spot immediately that there is no angle there. It's already written as a function of the momentum only. So capital L is constant, capital G is constant, capital H is constant. So semi-major axis eccentricity and inclination are constant. The orbit doesn't change its size, its shape, or the inclination relative to the equator. The angles move at some frequencies that can be computed from here. For example, I can put this equal to the sun's change in right ascension to have some synchronous orbits. Okay? Or I can spot that this term can be 0, in which case, for this value of the inclination, I have the so-called critical inclination that is used as a principle to put Molniya and Tundra orbits. In the restricted three-body problem now for asteroids, although I saw a few heads moving now, so I realized that most of the people are interested in satellites rather than asteroids. But that's in the restricted three-body problem, a way to write down the disturbing function is to write down Newton's equations of motion for three bodies in an arbitrary inertial frame, and then subtract by 2 to get the relative motion, and try to write the right-hand side as the gradient of a scalar function. These would have two parts, the Keplerian part for each of the two, let's say, smaller bodies, and the perturbation due to the other body. It's exactly what I showed you before. There is the direct term, which has to do with the distance between the two bodies, and the indirect term, which comes out from here because I'm moving to a non-inertial reference frame. So for the restricted problem, the Hamiltonian will be this one, as I showed you before, in heliocentric coordinates now, and I have to change that into orbital elements. Again, please see the book of Murray and Dermot, but the starting point is the triangle here. R minus RT squared is R squared plus RP squared minus the product times 2 times cosine the angle. Invert that and raise to the power of 2 and do the binomial expansion. That's the starting point, and then you have to translate the angle psi to the other angles. It's, of course, much more difficult than it sounds. The end result is you actually produce a sort of Fourier expansion in the longitudes. I prefer to use the longitudes. Everybody prefers to use the longitudes. Okay? So the Keplerian is just this, if I write it in elements. And if I have many planets perturbing the asteroid, I have a sum over the planets. And for each planet, I have a Fourier series, which contains the elements of the asteroid and the planet. So you have here linear combinations of all angles. And you have here coefficients, which depend on the semi-major axis, eccentricities, and inclinations. And they are essentially power series. Of course, the semi-major axis paths can be conveniently written in terms of Laplace coefficients. But the rest we keep as a power series in in eccentricity and inclination, or sine of inclination half, if you like. Now, the main point here is that not all combinations are permissible. There are the symmetries and analytical properties of R that give you a set of rules that one has to follow in order to construct this expansion, and they are the so-called Dalander rules, of which the list is like that. It's actually, okay, because it's invariant under the simultaneous change of sign in all angles, then there has to be only cosine terms and only real coefficients. And the sum of all integers in the linear combination should be 0 because it has to be invariant under a rotation around the z-axis. The sum of the powers in the inclinations have to be even because it has to be invariant under a change of sign of both inclinations, and another set of rules for the other integers, NP and QR, which must be positive and even. This is a more tricky part. The original Hamiltonian has an essential singularity when R equals RP. Of course, collision. And if you translate it to elements, there are also, you see that there is some singularity because it's an expansion on the square root of the definite momenta, but this you can remove if you go into Cartesian coordinates like that, but only if the combinations of the coefficients is this one. This is very difficult to understand in an abstract way, so let me make it done. The 3-to-1 mean-motion resonance with a planet means that I am at some location in the asteroid belt, this is 2.5 astronomical units actually, where Kepler's law tells me that there is a combination of frequencies of the asteroid and Jupiter, which gives me a ratio of 3-to-1. So I'm looking for a term which is like that, okay? Which means this is -1 and this is 3, and the order of the resonance is 2. Now, the rest of the integers, because all the integers in the cosine have to sum up to 0, the rest should have should amount to 2, actually to -2, but that's okay. Then, I try to find what arguments could be there. Well, there is this one, which is the argument of the third one, -2 times the longitude of the asteroid. So 3 minus 1 minus 2 is 0. The same if I subtract 2 times the longitude of Jupiter, again 0. The same if I subtract 2 times the node of either body, or 1 and 1 in perihelia, 1 and 1 in the node. Now, in front of that, there is the power series in eccentricity and inclination. Given the rules, you know that the starting point is eccentricity squared because there is 2 here. Or eccentricity of the planet squared because there is 2 here. Or inclination of the asteroid squared, inclination of the planet squared, and of course there is higher order terms going in powers of 2. Okay? And there is a set of arguments that cannot appear in R, which is this, for example, because they violate the rule that says that the contribution in the node should be even. Okay? So this is a way you can, let's say, if you have some experience, smell what are the terms that are important or are not important in my problem. And for example, if you ask me, I want to study this for asteroids with a relatively small inclination, then I would also kill these terms because they depend only on the node, which means that if I take the derivative with respect to the node, I see no contribution in the eccentricity. Okay? So this is how one can play with the disturbing function, by collecting the arguments that are of interest to him, and then, by experience, let's say, try to find out which are the most important to keep in order to simplify the problem if he wants to treat analytically, or if he wants to understand what happens in a numerical simulation, what is real and what is wrong. So I think I'm going to stop here. If there are questions, it would be nice, and then we will resume tomorrow for the rest.
Thank you. Questions? Yes, again?
Yeah, in your expansion of the disturbing function, when you treat the mean-motion resonance like in the last slide, the fact of the matter is also that the resonances are not single locations in the sense that they have width and kind of drop off. So when you're looking at the strength of the resonances in this sense,
I haven't looked at it yet. I just glanced.
Okay, well, I was just wondering if there's a way to pick out easily, other than looking at the eccentricity term, the leading term, whether, let's say, the potential well that you're looking at is one that's going to capture or eject material.
I mean, you mean an easy way of knowing beforehand what will happen?
Well, I need to categorize whether it's like a stable or unstable.
Oh, no. I can tell you right away that if, for example, I do the approximation that the planet is moving on a circular orbit, then everything is stable.
Right.
That's satisfying idea, because it turns out that there is only one argument that you can keep in the list. It's this one, and one argument means one combination of angle, means I can do a canonical transformation to make it a single variable problem, and that's it.
Still, you have a stable solution and a subtle.
Yes, yes, of course. That's subtle. But they are long-term stable in the sense that inside the separatrices, or they don't move essentially outside the separatrices. But classifying beforehand which resonance is stable and which is not, it's basically not possible. Okay, you have to do the computation. But of course, the order of the resonance tells you something about the size. Okay, because of the leading term, essentially. Also, you have to take into account that there are the Laplace coefficients, which tell you that if you approach Jupiter is more important than when you're far away, but let's drop that for you. So that's what we can do. The rest we can see tomorrow. Okay? There is some sort of sketch you can do, but it won't be of much use.
More questions? So if not, I would like to thank Kleomenis again